Welcome back to lecture 21.1, where we're going to do Maxwell relations continued. Okay. So remember, we derived all of our Maxwell equations this time. I want to basically just dive right back into these Maxwell relations. Remember that these all involved combinations of our four thermodynamic variables, which, remember, are S, V, T, and P. Okay? So let's write down our central equation, which, remember, is just our first law written out in terms of exact differentials. So that was du equals T ds minus P dV. All right, so let's look at so obviously our central equation contains all four of these thermodynamic variables, T, S, P, and V. Okay, but I want to make some points here. So first, remember that since it's du, the variables are S and V, right? That is, U has natural variables S and V. You can see that because du is du, and it's got a ds and a dv. These are the differentials, right? Okay, so the other thing I want to point out is some relationships here. So first off, let's look at S and V. So here, S and V are they intrinsic or extrinsic variables? Right. So think about T, S, P, V. So if I double the system size, the entropy goes up. If I double the volume, so that's extrinsic. Whereas T and P are intrinsic. See how many other colors I have. Just one more. Now I also want to point out that these are thermal variables, right? I'm out. I'll just have to reuse blue. Whereas P and V are mechanical. Okay, so you can see quite some interesting relationships here in our central equation. These two are thermal variables, these two are mechanical, these are extrinsic, and these are intrinsic. Okay? So we have four variables, we have four possible combinations where you need one each. So four combinations of these thermal variables where have one each of mechanical and thermal. Right? That is, I can make four possible combinations where I have, let's actually mark it out again. So T and P So our mechanical are P and V, and our thermal are S and T. Right? These have to do with work, and these have to do with heat. All right, so how many possible combinations can I make? Well, I can make S and V. We already did that one. We can do S, and instead of V, that's going to be P. We can do T and V, or we can do T and P. And so each one of these combinations are the natural variables for one of the thermodynamic potentials. Okay, so which one's which? Well, we know that U was S and V. S and P was our enthalpy. So let's call this the internal energy. Or potential energy. This was our enthalpy. Our function of T and V was our Helmholtz free energy. Or Helmholtz potential. And finally, our Gibbs was T and P. So this was our Gibbs potential. Isn't it nice that the Gibbs was G, but the Helmholtz, unfortunately, H was already taken by enthalpy. So it's F. All right. So now I want to ask, why are these called potentials? There's no reason for that to be capitalized. Why are these called potentials? Why am I calling these the Helmholtz potential, the Gibbs potential, and the internal energy, why am I calling it potential? Well, there's a nice analogy with classical mechanics. So remember, in classical mechanics, if we had U, we called it the potential energy. And if we wanted a force was equal to minus the gradient of that potential energy. Remember what the gradient is? It's just all of these partials. So minus partial f, partial x dx, minus partial f, partial y dy, minus partial f, partial z dz, right? That means just in the 3 dimensions of space, these are the partials in each of those dimensions. So this is in 3D. Let's just, for simplicity, let's look in 1D. Then we had the force was minus d dx Whoops. Why do those say F? Those should say U. du dx. Just make that. So that's d dx of u, or we could write it like this, du dx, same thing. All right, so imagine a mass spring system. What was the potential energy? Well, it was U equals U is 1/2 kx squared. So what's the force? Well, the force is minus d dx of 1/2 kx squared, which is minus kx. Oh, remember, this is Hooke's law. That is, there's a restoring force for a mass spring system, right? So we know that if we get a potential and we take the gradient, we get a force. Okay, so there's an analog in thermodynamics. When we have a potential, for example, like U, so if U is the potential energy, remember what one of our derivatives of U that we saw last time was T. This is partial U, partial S at constant V. Remember how we got that? We compared our exact differential partial U, partial S, constant V, ds, plus partial U, partial V at constant S, dV, with our central equation, T ds minus P dV. So you can see T is partial U, partial S at constant V. So here you can see that now I have a potential. I take the derivative, the gradient of it, or the derivative of the partial derivative of it, I get the equivalent of a force. So you can see that temperature and pressure, because the pressure is also, right? So the pressure was minus partial U, partial V at constant S. These are our equivalents of forces. So you can think of it as if I apply a force to a mass spring system, I change the potential energy. Here, if I apply a temperature gradient, I will have some heat to flow. So I'll change the internal energy. Or if I have a pressure gradient, right, a change in pressure, I will cause the volume to change, right? I'll do some work. And I'll do some work, and so I'll cause the internal energy to change. So you can see this is why these things are called potentials, because there's this exact analogy. Okay, so let's stop there, and I'm going to actually recap all of what we've learned so far about our Maxwell relations.